probabilistic planning that will be presented by Scott Sanner. Thank you, Scott, for contributing to the school. Let me say just a few words about your work. Your research spans a broad range of issues from machine learning to planning and decision making. And your work has been recognized in particular for significant contributions to the topics you will be talking on today, the area of probabilistic planning. You have contributed to, you have proposed a system called RDDL that under representation and the language that you will mention during your talk. And you have worked on several applications beside what you'll be talking on today, such as recommender systems, smart cities, transportation, and optimization in transportation systems. Regarding your career, you started your career in Australia at the Australian National University in Canberra, then you joined the Oregon State University, and now you are a professor at the University of Toronto. So Scott, the floor is yours.
Okay, thank you. Let me turn my video on. There we go. Here I am. Okay, thank you for the very kind introduction. Yeah, so I'm going to talk about historically what I, if you look at my research recently, I probably moved a bit more in the applied direction in the conversational AI and so on. But I still am using the MDP methods and all these, all this work, but just in different applications these days. But historically, my work is in the area of MDPs and more generally probabilistic planning or planning under uncertainty, and that's what I will talk about today. So I'm trying to decide, an hour and a half. So Malik or Michael, I have an hour and a half, right?
Yeah, including questions.
Including questions, okay.
Yeah.
Okay, that probably means I'll skip some more of the detailed content at some point. But I also, it's hard to give an hour and a half lecture without a little bit of break. So at some point, I'm going to just take a 2-minute breather and let people get up and get coffee or do whatever you have to do, depending on where you are. And I'm not actually sure exactly when that'll happen, but I'll just do it by time. So wherever I am, about 12:45 for me, I'll take a quick break. Okay, so let me dive in here. So I'm not watching the chat, but if anything, Michael or Malik or someone else, if you do have a question, just a burning question that you want to ask, feel free just to unmute and speak up. I don't mind that at all. Having some interaction and be able to track the audience progress is a good thing. Okay, so without further ado, yeah. So I'm talking about probabilistic planning. And can you see my ink here?
Right.
Yeah, good. Okay, great. So I'm talking about probabilistic planning. For the most part, I'm going to focus on the mark optimization process. But initially, I want to discuss all the ways uncertainty can come into planning and ways that you might deal with it and model it. So in fact, I want to initially pop up and discuss the potential of a partially observed MDP, and then the assumptions we're making when we work with MDP, which is much more tractable. And I think many of you have experience and you already know a lot of this, but hopefully this is a good refresher. Okay, so what are my goals in this lecture? I want everyone to understand the ingredients of formal models in decision-making under uncertainty in general. It's a bit more broad than the talk title, but I just think it's good to have this bird's eye view of how to model problems that you care about. Right, and then we're gonna mainly focus on, I would discuss generic models and their properties, but we're mainly gonna focus on the MDP, right, and the fundamental solution techniques and the properties of those solution techniques. In an hour and a half lecture, I really don't have time to go into the state-of-the-art probabilistic planning, but I will provide you with pointers as to some methods that are quite effective for further reading. I'm not sure if I'm going to have time to cover Riddle. So now I pointed out that probably for the ICAPS community, probably one of my bigger contributions would be the design of this language as an alternative to probabilistic PDDL. For the simple reason that it allows you to model a more expressive set of problems than probabilistic PDDL. So I'll try to briefly cover that, but I won't have time, I think, to go fully in depth. But there is a language that backs a lot of what I'll talk today. And I will talk a little bit about why you might want to use riddle as opposed to probabilistic PDDL for probabilistic problems. So I'm actually, sorry, these slides are recycled from 2018. I believe this stuff will be covered in later lectures, but I actually failed to look at the schedule this year to verify that. So I hope this stuff is covered later. If not, I'll provide pointers. Okay, so planning on uncertainty in general. I do want to distinguish critically, right, planning from reinforcement learning, although they are two sides of the same coin, right? So, in planning, at least in deterministic planning, we're computing sequences of actions, right, to obtain occasional rewards. This is a decision theoretic approach where you have costs and rewards, and you're trying to maximize perhaps the accumulation of them over time. But critically for planning, right, we have a known environment, and for uncertainty, typically we're going to assume it's stochastic in a probabilistic way. There's also possibilistic as well. I guess saying it's stochastic is a bit of a strong assumption here. I don't think that would typically be true, but I think it's where the majority of the work lies in this research area. But the key thing, planning you have a known environment, right? So what's reinforcement learning, right? You don't know the environment, you don't know the model. The only way to understand it and how to act is from sampling in the environment. And so now you have an unknown model, right? But you can sample from it, right? You can explore in the world or explore in your simulator to understand things about the world. And it turns out that the RL methods are just all sampling versions of the analytical planning methods. They're very related, but very different settings, right? Whether you a priori know the model or not. And in the ICAPS community, typically we're assuming that we know the model. So for the most part, I'm going to focus on the planning perspective today. Okay, so let me just discuss some things up front, some problems that you might want to model, and later we'll discuss exactly how you model them. So let's look at elevator control. I don't know how many times you have stood in an elevator and you're waiting, you're thinking, wow, it's like 2020, like why am I still waiting? In this bank of elevators. It's still in 2020, it's an important problem to solve. I think solutions are better than they were 20 years ago, but it's an important problem, and it's difficult because it's a concurrent action space, right? You have, if you have 6 elevators in an elevator bank, right, and each can go up, down, or open its doors, or stay, right? Let's just assume 3 actions, right? Then you get 3 to 6 actions. And you start to get sort of very complex, combinatorially explosive action spaces. So one thing that makes it difficult is concurrency. And back to my previous point about probably PDDL, one thing it doesn't handle well is concurrency, and that's always been an issue for me with problems that I've cared about. Whereas Riddle, as I'll briefly discuss, will handle concurrency natively. So the next point that we have here is that we have random arrivals. And these are exogenous arrivals. They occur at every floor, people arrive randomly, and so on. And they're all independent or roughly independent events, right? In fact, for arrivals, you'd probably think of a Poisson distribution. But of course, like arrivals at the ground floor are different from arrivals at a mid-floor in a building, right? So it takes some effort to model these distributions. One thing is all of the stochasticity is roughly independent, right? And two things that probabilistic PDDL has trouble doing, if you know it, is concurrency and independent exogenous noise is just something that probabilistic PDDL cannot model. And that's where I designed the Riddle language. Okay, so FYI. So we'll get there later. Objective.
Sorry, Scott, to interrupt. What do you mean by concurrency in this context? Is that the concurrency of the actions?
Concurrency of the actions, yeah. So you have 6 elevators. You have an independent action per elevator, and so you get this cross product space for the action space. But every elevator can move independently, right? But with concurrent control over the 6 elevators at the same time.
Yeah, makes sense. Thank you.
Okay, good question. It's good to have to. It's good to get some feedback. Okay, so what's the right objective in this setting? Right, I mean, you might think, well, I just want to minimize the total wait time of everyone. But you think carefully about that. Well, that allows you to have one guy waiting on the 99th floor, right, and to give him a 5-minute delay because you're minimizing everyone else's delay or wait time, right? So we're looking at averages. There can often be a few people who really lose out in the average, and so maybe if you want to strong guarantees in elevator control, maybe the average wait time or the total wait time is not sufficient. And so you might think of like quantile approaches. Make sure that 90% of the people get at least this no more than 2 minutes wait time, etc. So the objectives can get quite complex here. I don't want to go into a whole lecture on modeling elevator control, but I do want to point out that objective design in general, as I think many of you will know, is an art, right? What is the right objective for an end problem? Typically it's multi-objective even. These are really challenging problems to solve. And the best thing about using optimal solutions to MDPs and so on is that they really are optimal with respect to your objective. And you often say, well, why did it do that? You're like, oh yeah, because it can kind of cheat and get high reward by doing this. And so you have to be very careful when you design objectives. It's not just give reward for everyone who gets to their destination. That's going to have some caveats. And finally, you might even want policy constraints in this domain, right? For example, people have told me this has happened to them. It's never happened to me, that you're in an elevator going down and then suddenly it reverses and goes up to pick someone up, right? As far as I know from most elevators, it's a policy that you shouldn't reverse direction if people are in the elevator and going in the current direction. And so you have some constraints on the policy. You could maybe do better control without them, but at the end of the day, you don't want really upset passengers. Okay, so that's elevator control. Seems simple, but there's a lot more to think about than perhaps you would notice. Historically, so let's move into another domain, 2-player games. Othello Reversi, right, highly combinatorial game, and it's a 2-player game, right, meaning your win is your opponent's loss. In fact, all these games here, Othello, backgammon, and Go, are 2-player games and zero sum, so your win is your opponent's loss. Very large action space for most of these games. Go has, early on, roughly 361 actions, because you can place a stone on almost anywhere on the board. So huge action spaces, which have made these problems quite difficult. And that's why, so often you'll see some element of learning and search, learning to estimate heuristic functions, and search to sort of sparsely search the game tree. So Othello Reversi, this was solved in the 90s with logistic regression search. By solved, I mean it beat the top human players. Backgammon had a value, originally solved in the mid-90s by Jerry Tesoro, and this solution involved a neural net as a temporal difference value estimator, and then a bit of search in the final solution, a bit of search, I think for 3-ply or 3 levels on top of that. And Go, as we know, was only really solved recently, beating the grandmaster Lee Sedol with, quite frankly, quite a lot of computational power. I think everyone's heard of AlphaGo and realizes that had policy learning, value learning for heuristics, and then multi-color tree search on top of that. And you see these hybrid methods in all of these winning solutions. Now that's 2-player games. let's look at other, not just two-player games. So multiplayer games like poker. Now here, here the award's more complex, right? I think what I want to say here, sorry. Typically when you go multiplayer, you might look at general sum games, which go beyond the zero sum case. So it may not be the case that one's loss is the other's win. In poker is a really difficult problem for the need to do opponent modeling, right? And I think all the winning solutions do some amount of opponent modeling, but they have to be careful that the opponent can change their strategy. So it's really nice, one thing about games in general is that the transitions are kind of adversarial, right? There's some other cognizant agent who is trying to shift the direction of the game, right, in their favor. Whereas, when you have just purely stochastic uncertainty, it's much easier to deal with because then you can just reason an expectation. But this one's hard because you have this very adversarial agent, very complex policy space. They can change their policies. And it's, I haven't followed poker in recent years, but I followed Mike Bowling's work for a long time. And he had sort of mixes of like Nash equilibria and best response strategies to kind of hedge against knowledge of the current strategy while trying to be robust to changes in strategy. So it's very complex solutions there. It's multiple rounds, it's sequential. It is partially observable, right? Because we don't see the entire state. We don't know what's in our opponent's hands. We might see their facial gestures. They signal in what they say, but again, it's very partially observable because what do the signals they send mean? It could be bluffs, etc. So very difficult domain, not one that I like to work with, but if Mike Bowling's work at Alberta has done a lot of work here, and Tomas Sandholm's work, Tomas Sandholm's group at CMU has done a lot of work. Okay, a lot of uncertainty here, but a lot of it's largely sort of opponent-driven uncertainty and partial observability from not observing the full state. And finally, I guess these slides are getting old now, but at some point the DARPA Grand Challenge was a big deal, and you think of the sensory input, it's highly partially observable. Right, and not only is it like sensor readings, like maybe a range finder in 360, but you can get whole images and video and so on. So the inputs are quite complex here. Model is clearly unknown, for different terrain. You might have approximate models, but you never know exactly what you're working with, how much your wheels are going to slip, etc. And so you have to, you need really robust solutions in these domains that can adapt very quickly. Okay, these are all problems that have high amounts of uncertainty from different sources, from adversaries and from just general, stochasticity in the world, and they're quite challenging. And these are the sorts of problems that we want to formalize. Now, we're not going to solve them all by the end of today's lecture, but at least it's good to formalize them and to know, if you can formalize a problem and say, oh, it's a POMDP, it's a decentralized POMDP, it's an MDP, then by just having that formal model, properties of the solution criteria. If it's an MDP, that a deterministic policy, a function of your state, suffices. If it's partially observed, then that you might need a contingent policy based on the history, or you might need a policy of a belief state. So, even though we often can't solve problems like POMDPs or DEC POMDPs exactly or optimally, given the complexity of the formalization, complexity of the solution, at least once you model it, what model class you're in, the properties of your solution. So when you're approximating, what you're approximating and what sacrifices you've made in your approximation. And I think that's always a critical thing to know. And one thing that kind of upsets me is when I see people dive into RL for a problem and they just, they throw everything into their deep QN learner, but they don't really realize, well, was the problem partially observed or fully observed? if it's partially observed, you really got to be careful about state aliasing. If it's fully observed, then you don't have to worry about that. And so, it's just important to think about how to model these problems up front before you go down and hack together a solution, because the properties of the solution will, and of your solution versus the optimal solution will tell you what you've sacrificed. So let's first talk about, in modeling, we care about observation, state, and actions, right? We've got a planning-oriented group here, so I'm not going to go too in-depth in discussing these things because I hope they're fairly straightforward, right? Actions are actuators. I think everyone knows what those are. We have observations, what this robot can see, but there can also be things the robot doesn't see, right? That would also count as the state, right? So there's often more to the state than what you actually sense, and even your sensing is stochastic, right? So you sense a measurement to the wall, but there's a lot of noise in that measurement. And so, again, the observations in state, the observation can be a subset of state, but even then the observations are often a noisy observation on the state. So you always have to think about what's a state, what's an action, what's an observation. Biggest problem I see, especially in RL, is people who conflate observations with state. If you know the state, then that's sufficient for acting optimally, if it's an MDP. If you only get observations, then you really have to think carefully, do I need to include the history of the observations to fully disambiguate the state? And I don't see that as often as I would like. Okay, so your observation set, right? Things can be like perceptions, distance from the car to the edge of the road, your opponent's bet in poker. And for states, right, it would be like the actual distance to the edge of the road, right? Not the observed, but the actual distance. And you might have a guess about what your opponent has as their hand in poker, but the actual state, which you may not know fully, right, technically knows what the state is. And so obviously, if you only get observations in practice, you're working with some sort of belief state. Okay, your action set. Actions could be concurrent. So just to follow up on the previous question, typically concurrency for me is when you have a factored action space and you have a cross product of those sort of factored actions. So if you're doing logistics, every delivery that you have to do is a different action, or every vehicle that you control, right, it has a different action space. It's independent of the others typically, and I call that concurrency. Now, all actions need not be under agent control. So right, there could be in like a two-player game. There could be like in poker Othello, right? You take an action, then the opponent takes their action. And so in this case, obviously the actions are under the opponent control. Now this is called, in poker and Othello, we have alternating turns, right? And this leads to like the standard game tree search that hopefully a lot of you have learned in your AI course. But that's only one type of multiplayer game where some actions are under the control of the opponent. The other case are concurrent turns, where if you think of like soccer or highway driving, it's not like in soccer, everyone stops, I kick the ball, and the person with the ball decides what to do and everyone stops, right? No, everyone's moving simultaneously, right? It's mass chaos. And every agent has to determine what to do, right, in this mass chaos to get their ball to the goal. Highway driving is the same way. You're merging right onto a freeway or highway, and everyone else is acting concurrently. If you know anything about modeling these problems, you know that alternating turns are way easier to work with in concurrent turns, because when you have concurrency in your action space, two agents move at the same time, you get like rock, paper, scissors, and you get issues of like equilibria and so on, whereas you don't have to deal with that in the alternating turn setting. And then finally, it depends on how you model it. You can model it just as noise, but there are things that could happen due to nature. Now, these are not, we're assuming nature is not adversarial here, it's stochastic, but people arriving for an elevator, right? You don't control this, but these things happen. You can think of them as actions, you don't have to. The arrival of mail, the failure of equipment, right? At the very least, be aware that there are lots of exogenous events and real problems that you don't have any control over. Sometimes you can model these as actions under someone else's control, either nature or other opponents. Okay, now if they're completely uncontrolled in the case of exogenous events, right, you might just model them as random variables. So you don't need to necessarily think of the exogenous events as actions. Okay, now we have to connect the observations to the state, right? And we have, three scenarios that we could be in, right? If you're not observable, right, then you observe nothing. I think if I'm correct in the naming, I think conformant planning is like this, right? You're like, you don't really get any observations as you plan. And there was a POMDP problem back in the 90s called Heaven versus Hell. And and the idea is you sort of have to go through this this problem, and at the end you make this binary choice, and only once you make it do you find out whether you made the right choice, right? I think so that was a case of a non-observable domain, right? You make the best choices in life, you get to the end, and you find out, oh, did I make the right choice? Okay, so less extreme than non-observable would be the fully observable case. In fact, the other opposite of the spectrum, right? This is the case we're largely going to focus on today with MDPs, right? When your state is fully observable, right? What you observe is your full state. And that leads you to the MDP case where a lot of work lives. Many board games, Othello, Go, and so on, you see everything about the state. Obviously, games like poker and so on are clearly not fully observable. So then you got partially observable, right? All remaining cases. You got stochastic observability, observing a subset of the state. Driving a car, right? What's your real position? You only know approximately. What's your opponent's hand in poker, right? Anything in the real world, right, is typically going to be partially observable. Of course, we're going to get to the POMDP here in a while. And although it's very hard to solve POMDPs exactly, it's just good to know that this model exists and what the properties are. So at this point, we've covered action, states, and observations. But now we need to have functions and map between them, right? Okay, we need to be able to model previous and future states, right? Conditional actions. We need to tell how states and observations relate to each other. And then we also need, eventually we're going to need a reward function to tell us what we're trying to optimize when we actually act. Let's go there. Okay. So, you probably know that typically we need to model if we're in state S and we take action A, what's the distribution over the state S prime, typically in an MDP setting, right? Or actually even a POMDP setting, which also has a transition. You're going to assume that the next state distribution is conditioned only on the current state and actions. We'll talk about the Markovian assumption in a minute. Okay, now typically when we do this, in most problems, we are assuming that the transition is stationary. That is, it's not changing over time. And that's critical because if your transition was non-stationary, you've got to model that non-stationary as well, which becomes quite painful. We're also assuming it's Markovian, right? The current state only depends on the previous state in action. Now, these aren't as limiting as they seem, right? It is possible to handle some elements of non-stationarity and some elements of non-Markovianness by reducing them to a stationary Markovian environment. And the way to do this is by augmenting the state description. So, for example, if we model, do I have it here? Yeah. So, if you think about elevator traffic differing throughout the day, right? I mean, think at 8 a.m. during the morning rush hour, everyone to the ground floor going up, right? And so if you've modeled arrivals, a state or accounts of people at each floor as state variables, then your transition has to encode the exogenous arrivals, right, of people at each floor. So your transition has to encode these random arrivals. But we know that the traffic in the morning, right, the arrivals in the morning at 8 a.m. are different than the arrivals at 5 p.m. At 5 p.m., most people are arriving throughout the building, floors, 2 through N, and they're going down to the ground floor. So clearly the transition is not stationary. And how do you get around this? Well, you simply augment your state description, right? with maybe the hour of the day or the the morning or afternoon or evening or so on, right? You choose how you model your state. But basically, if you put some state into the model for time, then clearly your transition, right, if it had a bit of time in here, then gets conditioned on time, right? Or however you model time. And so, so elevator control, right, if you didn't have time in your state, is non-stationary. It is probably non-Markovian. But again, if you augment the state description, you can often reduce things to, roughly be stationary Markovian. And that's the way we typically handle things in practice. And that's why typically these two assumptions are not as restrictive as they might first seem. Okay, so we've talked about transitions now. Let's talk about different rewards. Now, historically planning, just thought of achieving goals or not. And in this case, we if you're in the MDP setting, you might know that MDPs sort of require you to specify reward, and it suffices if you only have sort of a single goal to achieve and no cost, that you just have a reward of success and reward of failure, and as long as your reward of success exceeds your reward of failure, right, then that suffices for sort of goal-oriented planning. Typically, if you wanted to do goal-oriented MDP, you would just make the goal. There's two things that you could do. You could make the goal to be 1 and non-goal state to be 0. And the nice thing about doing this is that your value function actually under a policy has an interpretation of the probability of reaching the goal given the current state in the policy. That's if you model reward as 1 and the goal is 1 and failure is 0. And so it's nice to have this nice probabilistic interpretation to the value function. However, if you've ever heard of the stochastic shortest path problem, they model in that case, SSPs, they model reward as 0 and failure is well, okay. Failure is less than 0 because stochastic shortest path is going to get to the next point. I should have said this first. So stochastic shortest path also includes cost, and then it says reward is 0, and then cost is always negative. And then what you'll get is basically the shortest path and expectation to the goal. So if you don't have costs, then 1, 0 makes sense. If you do have costs, you probably want to take this SSP approach where the goal is 0 and the costs are negative. Okay, now not all problems have goals, right? Do I have okay? So and think in the MDP literature, we think of what are called continuing problems that are really never finished. Think of mail delivery or a mail robot. This robot has to go around, and whenever mail comes into the central office, it goes throughout the building and distributes the mail to the right people. And in this case, there is no single goal. You're never, I mean, if mail comes in 24/7 and people are in the office 24/7, I don't know, maybe a good academic office, right? People are always in at some time of the day. Then there really is no clear end to this process. So continuing problems or process-oriented problems. And in this case, you just sort of want to minimize the delay to when people get their mail. Or if you think of elevators, if you think of elevators as well, right? It's not like our goal is to get everyone on the ground floor because, well, there are always people arriving. And in these situations, it's harder to, elevators especially, I think it's a good example. It's hard to think about elevator control in a goal-oriented setting, right? So in this case, right, we have preferences over policies that are better than others, right? A policy that serves people faster and makes them wait less is better than others, right? And so here we get to the general sort of decision theoretic notion of MDPs, where we have a reward for states and actions, and we just want to optimize expected reward, right? And so we kind of get maybe like, we get a cost maybe for everyone waiting, right? So the cost per time step could be the total person minutes waiting time, and so on. And so there's really no clear goal here. We're just kind of trying to optimize this reward over time. It's just important to notice that there are these set of problems that are very different from goal-oriented problems. And in practice, the solutions can also be quite different, which is something I realized the hard way in my thesis. I had taken, in my early thesis work, I had taken work that was applied to process-oriented problems. And I tried to apply it to goal-oriented problems, and it didn't work. And I was cursing the guy whose work I was building on. But I realized, you know what, you actually want to use different solutions in these two cases. I don't have a whole lot of time to explain all these details, but maybe on Slack or elsewhere, I can explain kind of what changes and what you want to change in solutions. Okay, so we might get rewarded every time step, right? This is the immediate reward, but now a question is, we're getting rewards every time step. How are we going to trade off all rewards over time? Brings me to the next slide. And here's a simple example I give to prime this. Okay, let's assume you're in state. This is a two-state problem. Let's assume that you're in state s equals 1. And your actions are to stay in that state or to change. And then once you're in S2, it doesn't matter what action you take, you're staying in S2, right? And so let me go, sorry, I know there've been some questions, but I just, for the sake of getting through this lecture, I want to go fairly efficiently. But let me find the chat box so I can find it. And let me, or actually, I'm just going to ask someone to speak up. Hopefully not everyone will speak up at once. What action do you think is the best action to take from state s equals 1?
I guess it depends on the game.
So if I were to use game, I would be thinking of two-player or adversarial, and this is just a simple deterministic setting with two states and two actions. So I would just be a little bit careful calling it a game, because a game would be like a multiplayer, perhaps adversarial setting. But yeah, you are getting at the right point, which is that I haven't, this problem is underspecified. So can anyone articulate what additional information I would need to know? So by the way, I can't, from this view, I can't see the chat box, so I do have to ask people to speak up. What would I need to articulate for you to better know what the best solution is?
Hi, Scott. So a lot of people are saying to stay forever, and then if the horizon is infinite, and to stay unless the time is finite, and so on. Oh, and someone said to stay if horizon is infinite and the objective is to maximize the reward.
Yeah, okay, exactly. So the key, okay, this wasn't intentionally a trick question. And the question, like, depends on what game you're playing, is really the right sort of question to ask here, because it is underspecified. So the horizon matters, right? If I'm only acting for one time step, clearly you want to change, right? But if I'm acting for, okay, so let's say I'm taking the sum of rewards over time, because it is critical, of course, to say, well, I've only given the immediate reward. How do I combine rewards over time? So let me just take a naive sum. Sum rewards over time. Sorry, this is hard to read. So if I sum rewards over time, and I said my horizon was 10, what's the optimal solution? Sorry, if someone can read the chat or let me know. I don't know why I can't see the chat in this view.
Yeah, stay until the last step and then you change is what everyone is saying, along as me as well.
Yeah, precisely. Yeah, so and this is really interesting, because your policy pi is horizon dependent, is horizon dependent, right? The way you act when you have one decision left to make before you terminate is different than the way you act when you have more decisions, right? So you are going to want to get these +2s as long as possible, and then when you know you have your last decision, then you want to diverge and choose the change. And so the point, if you're in a finite horizon setting, right, for the finite horizon, then you need a time-dependent policy, which is really quite annoying to model, actually. So of course, the other choice is that the horizon could be instead infinite. And we'll get to this later. This has a nice property that because you have as many actions to take tomorrow as you do today, your policy shouldn't change, right? But if the horizon is finite, then you actually do need a time-dependent policy. I think this is a good example. Now, here we sum rewards over time, right? You could now, but there's one question, which might. Do I have it here? Yeah. Okay. So now here's the next question. I give I give you two choices. I will give. Okay. Now I give you two choices. One choice is $100 today. $100 today. And the other choice is I give you $100 on October 14th, 2021. Okay, are you ambivalent between those two options? I'm hoping people say no. I hope people would much prefer the $100 a day than $100 a year from now. Now, there are various reasons for that, right? I may not be trustworthy, right? So you'd rather just take your money and run with it. But assuming that I am trustworthy, that I would give you the money a year from now, right? If you still prefer the money immediately, the point is you don't naively reward, or your objective is not just the simple sum of rewards. Because if your objective was the simple sum of rewards, right, you would be indifferent between the same amount today versus tomorrow versus next year. So how do I better model, or what's one way to better model the fact that I prefer $100 a day? So we have to have some MDP people in the audience who know what's done in MDPs. Okay.
Discount future rewards.
Yeah, exactly. So that we have discounting, we basically say T steps in the future is discounted gamma to the T, where 0 is less than gamma, less than or equal to 1. And obviously if gamma is 1, then there is no discounting, but if gamma is less than 1, then tomorrow's reward is, if gamma is 0.9, then the $100 tomorrow is actually worth $90, right? And so there are ways: inflation, interest rate, failure of the process to continue. There are many motivations for discounting. But there are other things that you can do. You could now there are other criteria like average reward, but average reward doesn't really trade off. Average reward doesn't say anything about the fact that tomorrow's reward is less than today's reward, whereas discounting does handle that. But there are even criteria like min-max criteria, right? I want to maximize my minimum reward over time. So you can get really quite complex solution criteria. In general MDPs, you're probably familiar with the fact we use expected cumulative discount reward. It's a pretty standard solution. It makes a lot of sense for most problems. Okay. Right. So if you want to trade off immediate versus future reward, often we use this discounting, but that's one of many criteria. And there's a whole cottage industry of papers about how to solve MDPs and our different solution criteria. Okay. So what matters is the horizon. Is it finite or is it infinite? And are you looking at like average return or discounted cumulative return? These are probably the two most common methods of looking at rewards. And if you're looking at discounted, then you have specified discount factor. Okay. Good. So now, okay, we're kind of at our, we have lots of our model components specified. We have our action space, our state space, our observation space, and you know, typically these are modeled as, you know, as variables or fluents in planning parlance. Then we have transitions that tell us, you know, how our actions affect states over time. Now these are states, not observations, right? The only thing the observations tell us is some information, right? We know the state and the action generate the observation. And so we have an observation function that tells us, you know, what's the probability of observing different observations given we knew we were in the state of action. And that, of course, leads to MDP formulation, which, you know, would literally take like a 6-hour lecture to really cover in its full depth. So I just want to mention they exist. And then whether MDP or POMDP, you have a reward function. Transition function typically is stationary Markovian, and not as limiting again as they might first seem if you augment the state. And finally, what, you know, okay, here's your immediate reward, but what's your overall objective for how to trade off rewards over time? Okay, now, next question is, right, are all of the above known or unknown? I mean, there's a whole class of problems here. I think I'm trying to think here. So, and let me give you. There's actually one. There's actually even one class of problems where the states are unknown. So I worked with a researcher in Australia named Marcus Hutter, and you know, and initially when I started working with him, I thought he was working models where you don't even know what the state is. The partially observed, you don't even know what the state is, and so therefore he had to work with observation histories as the only way to have an approximation, or to have knowledge of the state. And so if you know Marcus's work, he has this ICAPS model, and that's also been explored a bit in DeepMind. Some of his former students, or Shane Legg, I think, co-founded DeepMind, Mark's former student. So there are some really extreme cases where you don't even know what the state is in your problem. You only know what you observe, and that leads to some complex models like ICAPS, which I won't go into here now, but it's fascinating if you want to look into it. Let me go a bit more traditionally. We have issues like, you know, if the model's known, right, you know the observation, the transition, the reward function. That's pretty standard planning under uncertainty, right? If you just have transition reward, right, then so typically we assume we know what state's actions and observations are. SA known, and observation space is known if needed. So you know, I'll be clear that probably Marcus Hutter is the only person in the world who actually has gone as far as to say, what if the state's not even known? You can't even model it. Which is probably true in practice, right? If I model real-world problems, you know, I don't know what exactly is the entire state. You know, what's the spin state of the of all the atoms in the core of the Earth right now? Might affect me in the future. I have no clue. So it is true in the real world, you might not actually know the states, but in most problems we model that are much, you know, less ambitious in scope, we're going to know SA, and if it's partially observed, we'll know O. So these things are, I'm assuming, are known, right? And then, you know, if we have known transition reward, then that's an MDP. And if we also have an observation function and we know it, then it's a POMDP. Okay. Typically, I'd say, now, I mean, I come into this community more from the MDP history than from the planning history. But from what I gather in talking to planning people, like they're very used to using, I think, a goal-oriented view of the world, right? Which is not always the way we would use or think about MDP or POMDP problems, especially if we think about infinite horizon. And so typically, is, you know, I'm not sure if this word's still in use, but maybe 15 years ago, people would talk about decision theoretic planning when you had a general reward and you wanted to maximize the expected utility, right? Decision theoretic and maximizing expected utility go hand in hand. Okay, now we go to the other extreme, right? You don't know one of your observation, transition, or reward functions, right? In this case, you're really in the space of RL, and it's still MDP or POMDP, but you have to use different solution methods here, because you can't just crank analytically through the model because you don't know. You have to sample it, right? So here it's a sample, and that's the crux of all the RL methods. And you have to interact with the environment to obtain samples, and that can be risky sometimes, right? Do I have to fall off a cliff 10 times to realize it's a bad idea, right? So anyways, I left out to the RL, to the reinforcement learners. Most of my work is model known. Now, obviously, you can kind of interpolate between these two. You could use your samples. You can use your samples that you collect to learn a model, right? And in that case, you'd be in like the model-based RL setting, where you will learn an approximate model and then try to planning the model to help your reinforcement learning solution, act more safely and explore better with fewer samples. Huge area of research these days. For a while, a lot of RL was model free. I'm very happy to say that these days, a lot of RL is going model-based directions because they've realized the importance of the model for reducing sample complexity and reducing risk and increasing safety. And so, it's a great opportunity for all the planning community, right, to take all these techniques that we've developed over the, last 30 years and to bring these to bear, right, for model-based RL. And by the way, we have the planning and learning track at ICAPS. If you're working on papers and you're doing work at the intersection of RL and planning, this is a great place to submit it. How does planning help RL save samples? And if your samples are lives, save lives. It's not just academic. Okay. Okay. Again, I'm going to focus on planning for this lecture, but I just want to give you sort of an overall sense of how to model general problems and what assumptions different solutions are making. These slides should be posted online, so you can look at this offline to review. If you've already had this view of the world, hopefully this refreshed it, and if you haven't had this sort of bird's eye view of the world, hopefully this helped fill in some details that maybe you were missing previously. MDP is the subset of states, action, transition, reward, right, along with your objective. Typically not drawn in the tuple. And the POMDP, of course, adds in the observations. If you have the observations, you're also going to need an observation function. Okay, so you have MDP or POMDP, and you either know it's either parts are known or unknown, right? And now once you know these things, right, you can start to characterize the solutions. And once you know the solution space, then you know how to officially find them or officially approximate them. That's just critical high-level knowledge that you should have. Okay, I am at 12:56. Let's take a 2-minute break, bathroom break, coffee break, whatever. But just because I am obviously taking a lot more time than I expected, we're going to start back in 2 minutes. Okay, so let me see what I can get through here. Just some fundamental properties of MDPs. And where's my lecture? Come on, try again. Screen. There we go. Okay, can everyone see the screen?
Yep.
Good. Okay. So now we're going to focus on MDPs. These underlie, I'd say 90% of planning on uncertainty papers at ICAPS. Okay. So I'm going to use this very simple MDP example to drive discussion. So this is sort of the probabilistic finite state machine view of the previous question where I asked people what's the best policy to take, right? We have two states, state 1, state 2. If we stay, now we made it stochastic. If we stay, then there's some probability of returning to state 1, of 0.9, but some probability if we stay of moving to state 2. we said once we're in state 2, no matter what action you take, you're always going to, with probability 1.0, just loop back to state 2. And if you change, right, you have probability 1.0 moving to state 2. Because rewards are state and action dependent, you'll see me draw the rewards on the arcs, right? If I stay, I get reward 2. If I change, I get reward 10, so on. This is just a probabilistic finite state machine view of the MDP. Okay. And note, please note that here we're fully observable, right? We know our full state, and the full state determines the future. If we know our state and we know our policy, we can completely determine the trajectories that are going to happen or be possible in the future. Okay, so here, state is just the set of 1, 2. Action is just the set of state change. We have no observations to worry with here. Reward is just, for example, reward of state equal 1 and action equal state is 2, and so on. Okay. Transitions, what's the probability of transitioning from state equals 1 with action equals state to state equals s prime equals 1? What we said was 0.9. Right. Okay. So it's easy, given a diagram like this, to write down SAR and SAT and R, right, which is exactly what we need to specify the MDP. Okay. Now we need to specify how to act in the MDP, and for that we have a policy pi, and policy pi maps states to actions, and we'll talk about properties of that in a second. Okay, so we're back to this question of what's the best policy, and we discussed previously we want to maximize. We need some way to consider horizon and to accumulate the rewards over that horizon, and often probably again 90% of the papers on planning uncertainty at ICAPS would be MDPs, and then 90% of those papers would typically take expected discounted reward as their criterion. It's the most common criterion that you'll see. And so formally, right, you're going to write this like this. And I have to say, I mean, if you're a mathematician, you're comfortable with this. If you're not, if you have like more of an engineering background, then you're always like, why is this, why all the math? Well, it turns out, I mean, this is a very convenient way to write down what exactly we're trying to optimize here. And if you've read the Sutton and Bardo book, I haven't read, honestly, I read the one from '98, I mean, the new one's more up to date, but also a bit longer, whereas the original one from '98 was very succinct. I mean, beautifully succinct. You could read it very quickly and get a lot of information. And what you'll see in that book, especially from '98, I'm sure still in the 2018 version, is just very beautiful manipulation of this expected value to derive all the solutions that you would see in the MDP. And I know of no book that does it better than Sutton and Bardo. So if you haven't read that book, do have a look at it. But this is more than just sort of some abstraction of what we're trying to do. This is really useful for manipulation. But what are we? So basically, what this says is that we're taking the expectation of some policy, which is determining our actions. We start in some initial state S0, which is our initial state, and if we know our policy, we know our initial state, that generates random trajectories, right, over some time horizon from t to infinity. So this is going to be an infinite horizon domain. And for any of those trajectories, we get some reward at time step t. And if we're discounting, right, we're going to discount that by gamma to the t. So it's just an expectation over the trajectories induced by the policy and the initial state. And in fact, you can manipulate this a lot to derive different RL solutions. So that's formally what we're doing. When we maximize expected discounted reward, expected discounted cumulative reward. And now, right, with this, we can say, well, what is the optimal policy, right, under this criterion? Well, and I say surprisingly, because you have to prove this, there does exist an optimal policy pi star such that there is such that the value that you can achieve under pi star for every single state, all states, right, beats all other, right, is greater than or equal to, so it could match, but it matches or does better than all other policies possible. So basically, you don't have to care kind of where you started to know which policy to take, a single optimal policy that only needs to look at the current state is sufficient for optimality. Moreover, right, a deterministic policy pi star suffices. You don't need to hedge your bets. You don't need to take probabilities over actions in each state to get an optimal policy. You can be deterministic. I always take this action in this state. I always take another action in a different state. So these are some nice properties that you can prove. There's a single policy that's optimal for all states and it's deterministic. And that should be contrasted with things like two-player concurrent games like soccer, where you have to consider things like equilibria, or think of rock, paper, scissors, right? You know, we all know that the optimal strategy there is the natural equilibria where you play 1/3 rock, 1/3 paper, 1/3 scissors. That's an example of a stochastic policy, right? And you need stochastic policies when you're in multi-agent settings to, you know, basically find appropriate equilibria. But in the non-multi-agent case, right, where you only have nature as the environment and it's stochastic, then a single deterministic policy suffices, which is a beautiful result. Because if you know you're in this MDP setting, you know that you can limit yourself to these policies and you could be optimal. Okay. Multi-agent MDPs, POM-DPs, multi-agent POM-DPs, they all have different solution criteria. And, you know, if I had another 4.5 hours, I could tell you more about that, but not today. Okay, so now let's talk about this. Let's talk about the greedy policy pi v. So there's a bit of math on these slides, and again, you can go back later and look at this more in detail when the slides are posted. But this is a very important solution concept. You know, the greedy policy. So the greedy policy is the policy that tries to optimize, that acts in a way that optimizes v for the future. So the basic idea is, let's assume that we could achieve v at state S prime. So if we only get to state S prime, then we can achieve v. Now, how would I act to best achieve v at S prime? Well, in my current state, I have an action that gives me some immediate reward. And then that action also gives a distribution over states S prime, right, where I can then evaluate the v of S prime, but there's a probability of reaching every possible next state, so I need to take sort of an expectation or multiply the value in each next state by the probability of getting there. And so, you know, you recognize I'm starting to build the Bellman backup here, and we'll get there in a moment. But the best thing that I can do to achieve v from S prime is to take the best action A, gives you the best immediate reward, and gives you the best state distribution to maximize the expected value of v in the next state. And whatever argument, right, whatever action argument that maximizes this quantity defines the best action to take from state S to achieve value v. This is a really important concept. So if you know how to act to obtain v from S prime, then pi of v guarantees that you will get v in expectation, or at least v in expectation, and that's a beautiful result. Now, another property that is important to know is that, well, when you're approximating value functions in practice, in some cases, especially in model-based MDPs, you have a choice between whether you want upper bound or lower bound. I don't think we have time today to discuss it, but basically, if you initialize your value function as upper bound, a lot of solutions preserve the upper boundedness. And if you initialize your value function as a lower bound, then your solution preserves the lower boundedness. And the beautiful thing about lower bound policy is that you know that if v is not optimal, but you know it's a lower bound, then this greedy policy pi guarantees at least that much value, right? So it's a it's a strong guarantee. And it is often why in MDPs, I'm sure in planning as well, why people like to work with lower bounds, right? It gives you strong guarantees. Upper bound, you know, I'm going to play the lottery and win. Well, good luck, right? But the lower bound you can trust for obvious reasons. Okay, so now, you know, everyone hopefully has heard of Richard Bellman, and you've hopefully heard of the Bellman backup. I think a lot of my audience probably knows it, maybe some don't. And, you know, Richard Bellman was no doubt a brilliant researcher, right? Started off, you know, the field of optimal sequential decision making under stochastic uncertainty. But I mean, in retrospect, I think I want you to see that Bellman only pointed out the obvious. If Bellman hadn't existed and Smith, some guy named Smith had instead, you know, worked in the same area, we'd be calling it the Smith backup, right? It's just because this is the Bellman backup is a very straightforward, very obvious thing to specify and derive. You can derive it from first principles. There's no point memorizing it. So let's talk about how we can optimally solve an MDP through a process called value iteration, which uses this thing called Bellman backup. And let's discuss where this Bellman backup comes from. So let's imagine that we're acting for t stages, and I give you a value function that I tell you is optimal for t-1 stages. So if you can just act in the current stage, here's a magical value function that will give you the optimal value over the next, over the remaining stages of your decision horizon. Okay. So now if I gave you this t-1 optimal value function, how would you act optimally with respect to t decisions? Well, it's kind of the same reason I had before for the greedy policy. So now we're looking at values. Now YQ, I think some people say it's the quality of an action in a state. That's the best explanation I've heard for the use of Q value. So we know we can achieve VT-1. This is given to us. We know the transition function. We know the reward function. All we have to say is if we took action A in state S, right, then here's the immediate reward. Here's the expected future reward that we would get. Right? There's nothing to optimize here. We're just making a computation. And that's the quality taking action A in state S. But now, of course, well, we don't care about the value of all actions. We care about the value of the best action. And so now the next step we're going to say is, well, what's the best action that we can take, right? What's the best Q value that we can take at time t? And once you do this, right, you derive the value function. And the cool thing is, given VT-1, we have now determined via simple inductive reasoning what VT is, right? And of course, pi t, how should we actually act, is the argmax of this. Argmax over A and A. So we not only know the best way to act to achieve VT-1, but we also know the value that we achieve because we're going to plug this in inductively. And so the question is, well, if we want to be inductive, if we only knew V0, then you can kind of see inductively, if you know V0, you can derive V1. If you know V1, you plug it in here, right? And you derive V2. So if we only knew V0, we could just inductively work backwards and come up with the optimal policies over all time horizons and optimal value functions over all time horizons. And you might recognize these two steps as the Bellman backup. And so the question is, what is V0? Well, I guess the simple answer is if with 0 stages to go, there are no actions to take, right? Then typically you're just going to assume V0 equals 0, right? You took no actions, therefore you got no reward. And so, of course, your setting might actually give a value, for being in the t equals 0 stage. Whatever it is, you know what the answer is. There's no decisions to make. It's just a fixed constant. And so we actually know what V0 is, and so we can work backwards to find out pi t. Remember, we're finding a horizon here, so we actually have a time-dependent or horizon-dependent policy, which we need for optimality. But we get both VT and pi t at all stages t. Okay, and again, like this is just inductive reasoning. This is Bellman backup, and it's straightforward. And again, if Bellman didn't come along, we'd call it something else. Now, the really cool question is to ask, what happens when we get to the infinite horizon, right? And at the infinite horizon, then we can actually get rid of our time dependency, because as I said earlier, the way you act today is the same way that you act tomorrow. And what happens as the limit of t approaches infinity, you find that the value function actually converges to some value, which we'll call v star, right? Now, typically, you're going to need things like a discount factor less than 1 for this to happen. If your discount factor is equal to 1, then you need other conditions to guarantee that you don't get infinite reward. So there's a few conditions that hold here, but if your discount factor is less than 1, that's the easiest way to make this hold. Okay, so that's a nice property. If we just kind of, compute VT for large enough t, at some point we converge and we get an optimal policy for the infinite horizon. Optimal V and an optimal policy for an infinite horizon. Okay, and again, this solution here is known as dynamic programming for reasons that I'll explain in a future slide. Dynamic programming, you'll know maybe for different courses, sort of caching information. Well, this is very clever in how it caches and much more efficient than a naive tree search view in some ways. Okay, so you often see this notation in literature. You have v t minus 1, and then you apply a Bellman backup operator. This Bellman operator operates on a function, which is why we draw it like this. And then once we apply the Bellman backup to that value function, we get VT. So this is the Bellman backup operator. This is just the previous 2 steps of deriving Q and deriving the max over Q just collapsed into one single step without the indirection of Q. Q is often convenient to have though in practice, which is why we typically divide into 2 steps. And the beautiful thing is, right, there is this a unique optimal value function V star, an optimal greedy policy, right, that satisfies this fixed point, right? That at some point, additional Bellman backups are not going to actually change the value, and you reach the fixed point. And so the fact that a fixed point exists also gives you some nice solution, some alternative solution criteria that where you can actually search directly for the fixed point. If you know things like the linear program solution to the MDP, which I won't cover today, but the linear program solution directly searches for a value function V that satisfies the fixed point. It's quite beautiful. Okay, so one thing we know is that in a discounted setting, once you have V star, the Bellman error of V star, so Bellman error is basically just if we back up a value function and compare it to the pre-backup value function, and we look at the maximum error, or the maximum difference between those two, right? Then we call that the Bellman error. And we know the convergence that B of V star equals V star, therefore by definition, the Bellman error has to be 0. And in fact, you can prove that prior to convergence, every Bellman backup, that the Bellman error of the value function after backup is reduces, right? If gamma is less than 1, then the Bellman error is decreasing over time, and you can prove that the Bellman backup is a contraction operator, which allows you to prove convergence. Okay. Now this also, of course, suggests yeah. Okay. So the fact that you do get this contraction also leads immediately to the notion of the fact that if I just knew VT minus 1, I could apply the Bellman backup to achieve V, and eventually be the contraction property I know will converge. So you can approach it inductively and intuitively, which is how I initially approached it. You can approach it mathematically from the perspective of a contraction operator, and prove theoretically that it also must converge. Just 2 sides of the same coin. So let me just go. I want to get into some key solution concepts here. And then I'll switch over to Riddle and then find some quick questions. So I know this is high level. Perhaps you came into this wanting to learn how to go plan tomorrow at MDPs, and I'm sorry that I don't have time to go over that. But the fundamental issue I see with a lot of students I work with is that they know all the solution methods, but they haven't learned the fundamentals. And so whenever I teach this stuff, I will always start with the fundamentals, and I hope everyone has a solid grounding in that before they go on to solutions. So I do want to discuss, what's so beautiful about the Bellman backup, and why it's advantageous to maybe other intuitive approaches. And so Another way to think of the Bellman backup is in terms of tree search. So let's assume we have some value function. I don't know why it's a 0. I'm sorry here. That's VT. Let's assume this is VT minus 1. So let's assume we have VT minus 1, some estimate thereof. And we want to say, okay, we're in VT, how do we act? Right? Well, again, we have a choice of action. We can take A1, we can take A2. And we know whatever value we get for A1 or A2, we want to max over those two actions. But the question is, well, if we take A1, well, what value do we get? Well, again, here's where you get now a probability of going to state. You get, say, probably like a 0.9 going to state S1 or probably a 0.1 going to state S2, right? So there's probabilities for every transition to the next state. And then once I get the probability here, so once I get the next state, I get the value. So we can multiply the probabilities times the values. Then we can sum over the possibilities that we had here. And that gives us the Q value, and then we can max with the Q values, right? And we get the value of the state. And so you can very much think of the Bellman backup as one step of expect a max tree search. So if you, in your AI course, you've learned minimax tree search, right? I have two agents, I'm the maximizing agent, my opponent is the minimizing agent. And so you see max, min, alternating. In this case, there is no opponent. Our quote unquote opponent is nature. Nature is not adversarial. So instead we just take an expectation over what nature does. But this is expect max tree search. And so, if we can do it for one step, why not do it for k steps, right? I mean, we don't have to do Bellman backup dynamic programming. We could just do tree search. Now, okay, so let me. Right. So for example, you may have V0 here, estimates of V1, estimates of V2, and you're trying to estimate V3. And you can just sample paths through this tree and try to estimate, right, some approximation. You could do it exhaustively, but you can kind of see that the state space, the number of states you have to explore explodes exponentially at every time step. So you could do this exhaustively and compute the exact backup sort of with a tree search approach. The key thing, though, while that is correct, is that you get this blow up in the depth of the tree, right? And so I don't have time to go into it, but obviously you understand multicolored tree search is basically saying, AlphaGo, and then if you know Thomas Keller's work at ICAPS and AAAI, or he's done a lot of multicolored tree search for solving these problems, right? You don't have to exhaustively explore every single branch, right? You can Monte Carlo or sample branches, right? And now you get an approximation, of course, of V, because you are sampling, but it allows you to do sparse sample paths in directions that seem more promising, right? And that is the core of MCTS, and that is quite effective in practice, as long as you know the initial state that you're in. So let me talk about, in contrast, the beauty of dynamic programming the Bellman backup, right? The beauty of the Bellman backup is it is computing the optimal V3 from V0, but is doing it without incurring the exponential blowup that you would get if you did a naive search. And the trick here is dynamic programming. If you just cleverly compute things in the right order and cache the values, you don't need to recompute them. And so here, basically, if we know V0 for every state, then we can do this Bellman backup for every state, right? The max and then the sum. We can do a Bellman backup for every state to compute V1. And then we're going to cache. We're going to cache V1, right? And it doesn't matter how we got to state S1 with one stage to go, right? We're Markovian here. So the only thing that affects the value then is what we do in the future. So the point is, in this, I'm going to go forward real quick. In this exponentially large tree that I could draw out here, right? There's actually lots of values. V0 of S1 here is the same as V0 of S1 that I would get along a different branch, right? Because we're Markovian. And so if we're just intelligent and we cache these values, then we don't have to recompute them. And then we know V1, we can use V1 to compute V2. And so this thing that was an exponential blow up as tree search, it was exponential in depth. If you look carefully at the operations here, you'll see the Bellman backup is proportional to the time horizon, or number of the horizon h, right? In this case, h equals 3. Now we have, for every state, we have to, for every state, we have to look at maybe every possible next state. So there's an s squared there. For every state, look at every possible next state. And then we have to, for every state, we have to look at all actions. So there's an a. Yeah, so I think the Bellman backup or value iteration, right, has time complexity that's linear in the horizon, linear in S, well, yeah, quadratic in S, and linear in A. Unlike tree search, which is sort of, exponential function of the branching factor and the depth. And so value, they're both computing the same exact thing, but, right, value iteration does it much more efficiently. Now, but okay, so why do we use MCTS today? Like, why is value iteration king? Well, a key issue I want you to note with value iteration is that it solves for the value of all states. And when your state space is 10 to the 18th, good luck, right? So if you could solve it, yes, you could do it in this time, but when you're looking at like 10 to the 18th squared, have fun. So even that becomes intractable, especially in factor state spaces where the number of states really blows up quite quickly. And the thing that people notice in practice is that in practice, if you're willing to plan online, erase all this mess. If you're willing to plan online, then geez, I got 2 minutes. If you're willing to plan online, then the initial state you're in. There's no need to solve for 10 to the 18 states. You just solve for a single state, right? I'll let you figure out which one's easier to do. With the expense that, of course, you can only plan once you know the state that you're in. But then MTTS allows us to efficiently explore promising paths in that tree. And of course, you can actually reuse parts of trees over iterations, which makes this more efficient. Because once I get to a next state here, S2, I can reuse the tree, right, that I've explored previously. So in practice, in theory, value iteration is way more efficient. But in practice, when you're looking at solving for a single state versus all states, you're going to want to solve for a single state. And then when you're in a single state, you can't really do that dynamic programming very easily. You could do methods like RTDP, which unfortunately I just don't have time to go into today, given the time, that kind of mix elements of search and dynamic programming. But I would say probably most dominant these days is MCTS. And Thomas Keller has a paper called on what he calls the THTS framework. And I can't even tell you what that name stands for anymore. But it's a brilliant framework that subsumes MCTS. It subsumes RTDP, real-time dynamic programming. And it's a nice unification of a lot of different solution algorithms, and it suggests what tweaks get you which algorithm and when you might want to use them. So I see I'm out of time. I apologize I didn't get nearly as far as I wanted to get today. So what I'm not going to have a chance to discuss some tricks like RTDP. They'll be in the slides, and I did do some paper pointers in the slides. And I'm not going to get a chance to discuss Riddle, unfortunately. However, you will find if you just search online, there are some YouTube Riddle tutorials, and there's some good tutorial material at the Riddle website, which hopefully you can find by Googling. And there was a tutorial that we gave with some exercises at the 2018 summer school that you can look at. The students found very useful. But Riddle is basically a nice compact way to specify very expressive MDPs very compactly. Okay, with that, I'm sorry for going over. I will, if anyone can stick around for questions, I'll open up to questions.